Okay, so the next talk will be by Hünkar Tunç from Aarhus University, and he'll be speaking about sound dynamic deadlock prediction in linear time.
So hi everyone. In this work, we introduce a new dynamic analysis technique for finding deadlocks. And I will start with a simple example which demonstrates the problem that we are addressing. So here we have two threads. And first, thread 1 acquires lock L1, then thread 2 acquires lock L2. After that, thread 1 requests to acquire lock L2, while thread 2 requests to acquire lock L1. And at this point, neither of the threads can continue their execution, as they are both waiting to acquire lock that is held by the other thread. And this situation corresponds to what's called a resource deadlock. And there have been many techniques proposed to find deadlocks, and dynamic analysis is one of such techniques. So dynamic analysis works by first running a program and then checking the presence of bugs in the obtained execution. And this technique has proven to be very effective for finding concurrency bugs. And there have also been wide adoptions of this technique. And some of the most popular dynamic analysis tools are thread sanitizer, concurrent, and so on. And we can classify dynamic analysis techniques into two groups. So traditional techniques aim to find bugs by checking if the current execution exhibits the bug. And there are also what's called dynamic predictive techniques. And these techniques are able to find bugs not only if the current execution exhibits it, but also some alternative interleavings which can be inferred from the current execution. So let me give an example that demonstrates the concept of predictive analysis. So here we have an execution, and observe that there are no deadlocks in its execution. However, in an alternative interleaving, there could actually be a deadlock. So for instance, if thread 1 and thread 2 had both executed their first events, then we would arrive in a deadlock situation. So the main principle behind predictive analysis is to reorder the events of the observed trace with the goal of exposing a bug. So in this work, we study the problem of dynamic deadlock prediction, and we study this problem from both a theoretical and practical perspective. We first establish certain complexity results, which shows that we cannot solve this problem efficiently while maintaining full precision. And consequently, we design novel algorithms which strike a good balance between efficiency and precision. And our empirical evaluation shows that our new algorithms outperform the state-of-the-art. So the state-of-the-art techniques in this domain are called SecCheck and DERC. And in the case of SecCheck, the properties of this method is that it does not report any false positives, but the underlying algorithm has a high polynomial complexity of n to the 4, where n is the number of events in the execution. And this number in practice can be very large, reaching to be in the billions. And in the case of DERC, this technique is in theory both silent and complete, but it relies on heavyweight assembly solving. And in our work, we introduced the notion of sync-preserving deadlocks. And this notion also has no false positives, and our algorithm has a nearly linear time complexity, which means that we have a linear dependence on the number of events in execution. So one thing to point out here is that there are other dependencies, such as the number of threads and the number of locks in the program, but those parameters are typically significantly smaller than the number of events. So having only linear dependence on the number of events is important. And other than these ones, there are, of course, many other works which focus on finding deadlocks. For instance, one particular line of work focuses on finding potential deadlocks, but that notion contains false positives. So the focus of this work is on finding real deadlocks. So when we look at the steps of predictive analysis, there are typically two phases. So after we observe an execution, the first step is to find certain events which we deem as potential bugs. And at a later step, we check whether these potential bugs can be real bugs. And I will start with discussing what are those potential bugs in the context of deadlocks. So here, we have an execution where threads 1 and thread 2 acquired locks L1 and L2 in the opposite order. So potential deadlocks are this kind of cyclic lock acquisition patterns. But there's an extra condition that there should not be a common lock that protects these lock acquire operations. So if you look at this figure, there should not be such a lock L3 which protects these lock acquire operations, because this would mean that these two critical sections are atomic. And lastly, potential deadlocks are a necessary but an insufficient condition for an actual deadlock. So there might be certain control flow and data flow dependencies in the program which disable a potential deadlock. If you look at this figure again, such a read operation which takes its value from this write operation would disable this potential deadlock, because this would mean that we first need to execute the events of thread 1 until this write operation before continuing on the executing the events of thread 2. So in our work, we first established that even finding the potential deadlocks is an intractable problem. And to address this, we proposed an abstraction which groups together certain potential deadlocks to gain efficiency in identifying them. And we call this abstraction abstract lock graph. So here we have an execution, and it's abstract lock graph. So to reiterate, the purpose of this graph is to find certain events which can potentially lead to a deadlock. And the nodes in this graph correspond to certain lock acquisition patterns by each thread. And these nodes also contain a list of events that exhibit the associated pattern. And I will not go into details on exactly how this graph is constructed, but essentially, when a cycle is formed in this graph, this corresponds to that the events of the involved nodes are potential deadlocks. And an important thing to observe here is that a single cycle may unify multiple potential deadlocks. So for instance, here we have a cycle, and this single cycle unifies two potential deadlocks. And by grouping the potential deadlocks together in this way, we gain efficiency in identifying them. But of course, this lock graph is only a heuristic, so there can still be exponentially many cycles in this graph. But in our experiments, we observe that this is often a good abstraction. So once we identify the potential deadlocks, we can now check whether these are real deadlocks. So here we have an execution where the events 3 and 8 form a potential deadlock. And this pair actually corresponds to a real deadlock. And we have a reordering of the events of the observed trace that exposes this deadlock, as shown on the right. So this trace on the right is called the witness trace. And there are, of course, certain restrictions on which kinds of reorderings are allowed. And I will, again, not discuss the details. But essentially, these restrictions guarantee that any program which generated the trace on the left can also generate the trace on the right. And once we have this guarantee, we can predict the presence of deadlocks even if we just observe the trace on the left. So previously, we established that identifying potential deadlocks is an intractable problem. And in our second result, we established that given a potential deadlock, performing sound and complete deadlock prediction is also intractable. So we cannot efficiently enumerate all possible allowed reorderings. And this typically implies that we need to consider a more restricted problem setting for efficiency, such as we can look for only a subset of all deadlocks. And the challenge here is that we need to restrict the problem in a way that enables efficient analysis while still retaining high precision. And to this end, we propose the notion of sync-preserving deadlocks, which is an adaptation of a notion proposed earlier in the context of data races. And one of the technical contributions of this work is to adapt this notion to the context of deadlocks. And this notion essentially has more conservative restrictions on which kinds of reorderings are allowed. And these restrictions allows us to devise efficient algorithms. So let me give an example that demonstrates the concept of sync-preserving deadlocks. So here we have an execution where the events 2 and 10 form a potential deadlock. And this pair, again, corresponds to a real deadlock, and we have a witness for it, as shown on the right. And in this witness, we simply drop all the events of the second thread. And we can observe that the order of acquired events on the same lock that occur in the witness are the same as in the observed thread. And this is essentially the condition that is imposed by sync-preserving deadlocks. And since this witness satisfies this condition, this is a sync-preserving deadlock. So in general, when we are looking for only sync-preserving deadlocks, we are limiting ourselves to look for only the witnesses that satisfy this condition. So in some sense, we have a smaller search space. So we discussed the notion of abstract loop graph and the notion of sync-preserved deadlocks. So here I will try to give some intuition on how these two things come together. So as we discussed before, a single cycle in our loop graph can unify multiple potential deadlocks. But if we speak in more general terms, a single cycle may unify exponentially many potential deadlocks. And then a naive approach would need to perform exponentially many checks per cycle. However, if we are only concerned with sync-preserving deadlocks, then we only need to perform linearly many checks per cycle. And moreover, if we employ a reordering algorithm which can find all possible deadlocks, then we need to spend exponential time per check. Whereas in the case of sync-preserving deadlocks, we only need to spend linear time per check. And additionally, sync-preserving deadlocks can be checked using an incremental algorithm. So we spend overall linear time per cycle. But of course, this efficiency doesn't come for free. We are essentially making an under-approximation with sync-preserving deadlocks. So an important question to ask here is that how much precision have we lost? We performed an experimental evaluation for our proposed technique, and we considered two settings. So the first setting is the offline setting, where we first run a program, then execute, then record the events that occurred during the execution, and then perform a postmortem analysis. And we compared our offline algorithm with both SecCheck and Dirk. Both these techniques are also offline, and the summary of the results are shown in this table. So we can see that both SecCheck and our algorithm found the same number of deadlocks, but our technique is significantly faster than SecCheck, whereas Dirk took significantly more time compared to the other two techniques, and he also found less deadlocks. This is because Dirk is based on heavyweight SMT solving, and it times out in certain large benchmarks. And we also performed a false negative analysis, and we concluded that only one actual deadlock was missed by our algorithm in this benchmark set. And this is based on the standard notion of bilateral reorderings. And we also devised an online version of our algorithm. So online here means that the analysis should take place while the program is running. And there exists no predictive method that works in an online fashion. And the existing methods that are non-predictive and online in this setting are typically try to find deadlocks by fuzzing the trace scheduler. And in this respect, another contribution of our work was that we were able to combine such randomized testing techniques with our prediction algorithm. So while analyzing a program, we inject certain delays in certain program locations with the aim to explore different program behaviors, and we're able to perform prediction at the same time. And we compared our online algorithm with a technique called Deadlock fuzzer, which fuzzes the trace scheduler. And in this setting, we let both our technique and Deadlock fuzzer run for the same amount of time per benchmark, and then we compared how many times each reported deadlocks. And the summary of the results are shown here. You can see that our technique had significantly more buckets compared to Deadlock fuzzer, and it also reported more unique bugs. So in conclusion, in this work, we studied the problem of dynamic deadlock prediction from both a theoretical and practical perspective. We first established the intractability of the problem, and we then introduced the notion of sync-preserved deadlocks, and we showed that this notion achieves efficiency and high precision at the same time, and it outperforms the state-of-the-art. And thank you.
Okay, so I'll add a question while we wait for other people to line up by the microphone. So what do you think it would take to deploy this bug detection technique in a bug detection system? And do you think it would catch a lot of bugs in real systems?
Yes. Okay.
Or could you say a little bit about that?
I think especially our online algorithm, because is more amenable to use in practice, I think. And we showed that in our experiments, compared to, for instance, the techniques such as fuzzing, it has comparable overhead. So I think this is promising to be used in practice.
Hi there, I'm Adrian Simpson from Cornell. I was just curious, like, given your work with the empirical evaluation, if you have any sense of like what kind of deadlocks this sort of technique could not find that are sort of like out there, but aren't predictable from concrete traces that are easy to find?
Mm-hmm. So certain deadlocks need to reason about the values of the events written and read. So to be able to find certain deadlocks, we need to reason about the event values somehow. And those deadlocks are sort of more difficult to find, and those are the ones that we miss by our technique.
Thank you.
Okay, let's thank the speaker again.